welcome to G-Fun Facts Online. For thousands of years, our study of other stars was a long-distance affair. We could look, we could analyze their light, but we couldn't touch. The idea of holding a physical piece of another solar system in our hands was pure science fiction. But that all changed in 2017. We discovered that the galaxy isn't a collection of isolated islands. It's a dynamic network, flinging entire worlds and the debris of their creation across the void. And sometimes, these cosmic messages in a bottle wash up on our shores. This has opened a brand new field of science, galactic forensics. We are no longer just astronomers. We are cosmic detectives, analyzing physical evidence to decode the secrets of alien star systems. This is the story of how we learned to read those messages. For a long time, astronomers predicted that if we ever saw a visitor from another star system, it would be a comet. Planet formation is a messy process. When giant planets form, their gravity acts like a colossal slingshot, ejecting trillions of smaller, icy bodies, comets, into interstellar space. The thinking was that one of these exiled comets would eventually wander into our solar system. As it neared our sun, its ice would turn to gas, creating a bright, hazy atmosphere called a coma and a classic tail, making it easy to spot. But the universe had a surprise for us. On October 19, 2017, the Pan-STARRS telescope in Hawaii spotted a faint point of light moving incredibly fast. At first, astronomers thought it was a comet, but it had no coma, no tail. It was just a bare, inert point. So they reclassified it as an asteroid. But the real shock was its path. It wasn't orbiting our sun in a closed loop like everything else. It was on a sharp, open-ended hyperbolic trajectory, a clear sign that it was not gravitationally bound to our solar system. This was the smoking gun, a traveler from another star. It was so significant that it got a whole new classification, I for interstellar, and a name, one I. Oumuamua, a Hawaiian name meaning a messenger from afar arriving first. Oumuamua was nothing like what we expected. It was small, just a few hundred meters long, and it wasn't an active comet. Its most bizarre feature was its shape. As it tumbled through space, its brightness changed by a factor of 10. This suggested it was incredibly elongated, maybe 10 times longer than it was wide, like a cosmic cigar or perhaps a flat, pancake-like shard. Nothing in our solar system looks like that. Then came the final mystery. As Oumuamua was leaving, astronomers noticed it was accelerating, being pushed by a force other than the sun's gravity. For comets, this is normal. Jets of gas act like tiny rocket engines. But Oumuamua had no visible jets, no coma to explain this push. An inert object with a strange shape that was somehow pushing itself. The enigma of Oumuamua sparked a firestorm of theories. One leading idea is that it was a fragment of a Pluto-like planet from another system, made of solid nitrogen ice. As it got close to our sun, the nitrogen would have turned into an invisible gas, providing the gentle push. Another theory suggests it was a water-rich comet, but one where cosmic rays had trapped molecular hydrogen inside the ice. The sun's heat released this hydrogen, providing thrust without a visible water vapor tail. And of course, the collection of anomalies led some to speculate it could be an alien artifact like a solar sail, though that remains a highly speculative idea. Oumuamua was the first messenger, but it wasn't the last. Its discovery opened the floodgates. Just 2 years later, in August 2019, amateur astronomer Gennady Borisov spotted our second interstellar visitor. This one, named 2I/Borisov, was exactly what astronomers had originally expected. It had a big, fuzzy coma and a long tail. It looked and acted like a classic comet. It was a relief, in a way. It confirmed that our models of planet formation weren't totally wrong. But when we looked closer, Borisov had its own shocking secret. Using spectroscopy to analyze the gas in its coma, astronomers found it was incredibly rich in carbon monoxide. The concentration was up to 26 times higher than the average for comets in our own solar system. This was a massive clue. And the gallery of visitors keeps growing. A third object, 3I/Atlas, was recently confirmed. Like Borisov, it's a comet, but it's even faster and likely much larger, maybe up to 20 kilometers in diameter. And when the James Webb Space Telescope pointed its powerful eye at it, it found yet another unique chemical fingerprint. While Borisov was rich in carbon monoxide, 3I/Atlas is remarkably rich in carbon dioxide, with a CO2 to water ratio among the highest ever recorded. 3 visitors, 3 completely different profiles. So how exactly do we perform this galactic forensics from millions of kilometers away? We have a sophisticated toolkit. The first tool is trajectory analysis. By tracking an object's path, we can calculate its orbit. If the path is a hyperbola, we know it's an interstellar visitor. The steepness of that path tells us its speed through interstellar space. By rewinding its trajectory, we can even figure out where in the sky it came from. This analysis suggests our 3 visitors come from different stellar populations. Oumuamua seems to be the youngest, from the part of the galaxy where stars like our Sun live. Borisov is older, and Atlas appears to be the most ancient, hailing from the galaxy's old thick disk. We are sampling material from star systems of vastly different ages. The most powerful tool is spectroscopy. By splitting the light from an object into a spectrum, we can see the chemical fingerprints of the atoms and molecules it's made of. For a comet like Borisov or Atlas, we can analyze the gas in the coma and directly measure the abundance of things like water, carbon monoxide, and carbon dioxide. This is how we discovered their bizarre compositions. For an inert object like Oumuamua, we analyze the reflected sunlight from its surface to determine its color and basic makeup. Finally, there's photometry, which is simply measuring an object's brightness over time. This is how we figured out Oumuamua's extreme shape and chaotic tumble, which itself is a clue hinting at a violent collision or a close encounter with its star in the distant past. So what do all these clues tell us about the homes these objects came from? The chemical composition acts like a cosmic thermometer. Different molecules freeze at different temperatures. Water ice forms relatively close to a star. Carbon dioxide freezes further out, and supervolatiles like carbon monoxide can only freeze in the absolute coldest, most distant reaches of a solar system. The extreme carbon monoxide in 2I/Borisov suggests it formed in an incredibly cold place, perhaps around a cool, dim red dwarf star. The high carbon dioxide in 3I/Atlas suggests it was well-baked, forming in a region warmer than Borisov's home, but still far from its star. And the nitrogen ice theory for Oumuamua? If true, it means it's a chunk knocked off an exo-Pluto, giving us direct evidence that such worlds exist around other stars. We can also measure isotopic ratios, different versions of the same element. These ratios act as a galactic birth certificate, linking an object to a specific type of star or region of the galaxy. If we find visitors with isotopic ratios different from our own solar system, it tells us their origin story was fundamentally different. The best part is, this is just the beginning. These first few discoveries were made with telescopes that weren't even designed for this. We are on the cusp of an era where finding interstellar objects will become routine. The Vera C. Rubin Observatory in Chile, set to begin its main survey in 2025, will be an unparalleled interstellar object hunter. It will scan the entire southern sky every few nights, creating a massive time-lapse movie of the cosmos. Scientists expect it to increase our catalog of interstellar objects from a handful to dozens, maybe hundreds. We'll finally have a large enough population to do real statistics. But observation from afar can only tell us so much. The ultimate goal is to get up close. This is where missions like the European Space Agency's Comet Interceptor come in. Scheduled to launch in 2029, this spacecraft will go to a stable point in space and simply wait. When an observatory like Rubin spots a brand new interstellar object on an achievable path, Comet Interceptor will be sent out to meet it. It will fly right through the object's coma, taking the first ever up-close 3D snapshot of a messenger from another star system. More ambitious ideas, like Project Lyra, are even studying the feasibility of launching a probe to chase down Oumuamua, using a complex slingshot maneuver around Jupiter and the Sun to catch up to our first, most mysterious visitor. The detection of these objects has fundamentally changed our view of the galaxy. We are not alone in an empty void. We are part of a vast, interconnected network where star systems trade material. Each visitor is a precious sample, a free mission to an alien solar system, delivered right to our cosmic doorstep. By continuing our forensic investigation, we're not just learning about distant alien worlds. We're learning about the universal processes that create stars and planets. And ultimately, we're learning more about our own place in the grand cosmic story. Thank you for listening to G Fun Facts Online.